Right, okay. So we are going to start the discussion of the RYM paper 6. There are 10 MCQs. So let's see what they have given in this MCQ paper. Let's quickly finish this one. So first question that they have given, the photochemical dissociation of chlorine molecule required 242 kilojoules per mole of energy absorbed from the light to break chlorine-chlorine bond. The maximum wavelength of the light beam that contribute to break the chlorine-chlorine bond. Students, they have given that in order to break this chlorine-chlorine bond, right? So we know that this is the chlorine molecule. They have given that the required energy in order to break this chlorine-chlorine bond is 242 kilojoules per mole. This is the energy. So they're asking, what is the maximum wavelength of the light beam that contribute to break this chlorine-chlorine bond? So we learned that in theories, in electromagnetic radiation theories, we have learned that how to calculate the energy of a photon. We know that energy of a photon can be calculated using equal hc over lambda, right? So this is the equation that we use to find out the energy of a photon. But here you can see that they have given the energy required to break chlorine 1 mole, right? 1 mole of chlorine molecules. So therefore you have to understand that we have to consider here the total energy required to break 1 mole of chlorine molecules. Therefore we can rearrange this equation into E mole hc over lambda into capital L. We know that capital L means Avogadro number, right? So this capital E here, this is the energy of a photon. In this question, we can consider this is the energy of a molecule in order to break 1 molecule, right? But here they have given the energy required to break 1 mole of chlorine molecules. So therefore, we have to use the corresponding equation for that one. E mole is equal to hc over lambda into L. And now you can substitute. Lambda is equal to hc, capital L over E mole. What is the Planck's constant value? 6.626 10 to the power minus 34 joules seconds. Velocity of light 3 into 10 to the power 8 meters per second. Avogadro number 6.022 10 to the power 23 per mole divided by energy per mole 242 joules kilojoules per mole, right? So you can see that the units are cancelling off. Per moles, second per second will cancel off, right? And we can get that 6.626 multiplied by 6.022. I told you that Avogadro number and Planck's constant multiplication is 39.9 multiplied by 3. And this is divided by 2.42. Right? Kilo means we know that 10 to the power 3. So 2.42 can be written as here in this way. And then here we have 10 to the power value 10 to the power 5. Okay, joules. Then joules will cancel off. And in the numerator, what are the 10 to the power values we have? In the numerator, we have 10 to the power 8, 10 to the power 23. So then the summation is 10 to the power 31 minus 34. So therefore 10 to the power minus 3. Okay. Then we have here 39.9 multiplied by 3 divided by 2.42. 10 to the power minus 8 meters. Right? So you have to do the simplifications correctly in order to go for the answers in this way. Now you can use logarithms in order to go for the final answer. What is the log value for 39.9? 39.9 6010. 1 point. Log value for 3 is 4771. Get the summation 187 2.0781. What are the log value for 24.2? 24.2 log value is 38.30. That is 0 point. Okay. Now take the difference here. 3. And here we have 7. 7 minus 3 is 4. And here we have 9 again. 6. 1.6943. Now check the antilog. 6943 antilog. 6943. We can take 49. 4. 6 means 4947. 10 to the power minus 8 meters. So this is the lambda wavelength. But remember students, they have given the values using nanometers. So you have to convert this value into the nanometers. We know that how to convert this kind of value into nanometers. How do you convert that one? This is 1 point. So therefore 49.47. So we can convert this one into nanometers by, look at this one. The lambda wavelength value that you obtain is 49.47 10 to the power minus 8 meters. So therefore, we can write down this one as 494.7 10 to the power minus 9 meters. Right? I can shift the decimal point one time forward by converting this one as 10 to the power minus 9. And we know that 10 to the power minus 9 means nanometers. Therefore, answer is 494.7 nanometers. So this is the final answer for the lambda wavelength, the corresponding energy. So according to the given values that they have given, we can take that the most closest answer for this one is third one. Question number 1, answer is 3. Right? Very easy. So you have to do the calculation. Already we discussed this calculation in our theory class. Okay? Under the electromagnetic radiation. Right. Now let's move on the second calculation. Second question. Second question is related to the electron configuration. Yes, electron configuration we discussed. What is the valence shell configuration of arsenious 3 plus cation? They have given 5 configurations, and you are asked to write down, find out the valence configuration, valence shell configuration. Remember, students, valence shell configuration is always they asking about what the last part of the configuration, electron configuration, right? So therefore, since they have given arsenic 3 plus, first of all, let's write down the element configuration. Arsenic. So what is the arsenic atomic number? Can you remember that one? Arsenic is 33rd element, right? So therefore, we can write down electron configuration for arsenic is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3, 33, right? So here to here we have 10 electrons, and up to here 30 and 33. So this is the configuration of arsenic, element arsenic. Then they have given arsenious cation, that means arsenium 3 plus. Arsenic 3 plus, 3 electrons are removed. So therefore we can remove these 3 electrons. No? So that is the valence shell electrons. Then the configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. So 4p is actually 0. Right? So according to the given answers, we can tell that this is 4p0. Nothing is there. So therefore, the valence configuration, we can take that one as what? 4s2, 4p0. So this is the valence configuration of arsenic. Valence configuration. Valence configuration means the last part of the electron configuration. So question number 2 answer is second one. Very easy. Question number 2 answer is second one. Let's move for the third one. Third one, they're asking, which of the following has 6 atomic orbitals with unpaired electrons? 6 atomic orbitals with unpaired electrons, right? Then, what are the elements they have given? This is very easy. You have to first of all find out in which elements how many unpaired electrons are there. First of all, they have given nitrogen, then argon, iron, chromium, antimony. So nitrogen is 7, argon 18, iron is 26, chromium is 24, antimony is 51. Yeah. So the configuration for nitrogen is 1s2, 2s2, 2p3. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. Remember, students, we can reject argon. Why? In argon's configuration, we know that argon's configuration is very much stable. All the atomic orbitals are completely filled with electrons. So therefore, no unpaired electrons in argon. So therefore, without any issue, we can reject the argon element. Iron 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2 is the configuration of iron because that is 26. No? So when you count the electrons here, 10, 20, 26, right? And chromium, we know that chromium configuration is stable, very important, right? Because in order to obtain the greatest stability, the configuration of chromium is rearranging into 3d5, 4s1. But we know that expected one is 3d4, 4s2. But in order to obtain the greatest stability, the configuration is rearranging into 3d5, 4s1. So let's go with antimony also. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p3. 51, right? 10, 30, 36, 46, 48, 48 plus 3 is 51. So this is the configuration for antimony. Now they are asking which of the following has 6 atomic orbitals with unpaired electrons. We know that here nitrogen, the p sub energy level is only containing unpaired electrons. 2p3 means just 3 unpaired electrons are there. So therefore we can't take nitrogen. Let's go for the iron 26. Here you can see that except 3d6, others are completely filled with the electrons. So therefore we have to worry about the d sub energy level orbitals. 5 orbitals are there, configuration is 3d6. According to the Hund's rule, first of all electrons are filling to the same spin and then the 6th electron in this way. Then you can tell that how many unpaired electrons are there? 4. But here they are expecting 6 unpaired electrons, right? 6 atomic orbitals with unpaired electrons. No, we can't take this one also. What about chromium? Students, you can see that 3d5OS1. Yes, this is the answer. Because in the 3d5, we know that according to the Hund's rule, first of all, electrons are filling to the parallel spin 1, 2, 3, 4, 5. This is 4s1. So the s orbital is also containing 1 electron. And here you can see that there are 6 atomic orbitals with 6 unpaired electrons. So therefore, this is the answer. So what about antimony? Yeah, in antimony, you can see that others are actually filled with the electrons, no unpaired electrons except this 5p3. In 5p3, we know that only p orbitals are there and each orbital is containing unpaired electrons. So therefore, just 3. So therefore, answer for this one is chromium. Question number 3, answer is 4. Very easy. These are related to the electron configuration. Right. Let's move for the 4th one. Assume that an electron of hydrogen atom is excited to the 4th energy level in an experiment on the emission spectrum of hydrogen. This question is related to the hydrogen emission spectrum. Which of the following is correct regarding the electron transition if the electron first moved from the 4th to the 2nd energy level and then goes to the ground state? Ground state means the first principal energy level. That means they have given that consider an emission spectrum, the electron transitions which went for the high energy levels, that means fourth principal energy level, that electron is coming back to the second principal energy level, and from the second principal energy level to the ground state. That means actually here we have to consider only two electron transitions, right? So they have given that the electron is excited and it went for the fourth principal energy level. That electron is coming to the second principal energy level, and then that electron is going for the first principal energy level. That means two electron transitions that we have to consider, right? So let me draw the energy level diagram, then you will understand more. Look at this one. We can consider four principal energy levels in this way. So this is n equal 1, n equal 2, n equal 3, and n equal 4. So they have given us to consider electron transition which is from n equal 4 to 2, and then that electron, that means second principal energy level electron, going for the first principal energy level. Students, you can see that this electron transition is corresponding to n equal 4 to n equal 2. That means this line is definitely belongs to Balmer series. Neither. The electron is falling to the second principal energy level means definitely that electron transition belongs to Balmer series. Now look at this electron transition. This is n equal 2 to n equal 1 to the ground state, which means this is definitely belongs to the Lyman series. This electron transition belongs to Balmer series, and this is Lyman series. And what else we know? You can consider that when you compare these two lines, this line has the highest frequency and the highest energy. And we know that something, this is actually H beta. H beta. H beta means the green color one. Okay? So we know that H alpha, H beta, H gamma, H delta, which are obtained in the Balmer series. We can see four electron transitions in the Balmer series. H alpha, which is red color, H beta, green color, then blue color, and the last one is violet color, right? So H alpha means electron transition from 3 to 2, beta means 4 to 2, gamma means 5 to 2, delta means 6 to 2. So therefore here we have only 4 to 2. That means this is actually green color line. So according to the informations that they have given, these are the two electron transitions, right? Okay. Now let's go for the statements they have asked here. Correct statements. Number 1, H alpha and H beta lines are obtained. No, students, H alpha means 3 to 2. They have clearly mentioned that in the information, n equal 4 to 2 electron transition is obtained, not 3 to 2. If it is 3 to 2, we could have taken H alpha. So therefore, first statement is wrong. Lines in the Balmer series are not obtained. So then what about this one? So this line is actually belong to Balmer series. That is wrong. H beta line and a line from a Lyman series are obtained. Yes, that's correct. H beta line, which is related to the Balmer series, and then we have another line which is obtained as a Lyman series. We have two electron transitions. That's correct. I think answer should be third one, but let's consider the other two statements also. Lines in the Lyman series are not obtained. Wrong. We got one. Fifth one, the two lines that are obtained due to the electron transitions are the lines pertaining to the fourth energy level from the bracket series. So actually we don't have any lines related to the bracket series. Why? We know that Lyman series means the electron transitions which are falling to the first principal energy. Balmer means second. Then we have what is the electron transition series? Partial. Partial electron transitions are falling to the third principal energy. Bracket means electron transitions which are falling to the fourth one. So therefore, we don't have any bracket series electron transitions. Fifth one is wrong. Question number 4, answer is third. Very easy. That is very easy. Right, okay. Let's move for the question number 5. Sorry. The number of electrons in the last sub-energy level of the plus 4 cation formed from the element of the atomic number 43. Students, you have written the electron configuration now. You know about the electron configuration from hydrogen to barium. In the class, we have written the electron configuration up to barium, atomic number 56. Can you remember what is the 43rd element in the periodic table? So the 43rd element in the periodic table is technetium, right? So technetium, Tc. So they have asked the configuration of plus 4 cation formed by Tc. First of all, let's write down the element configuration. Tc, technetium, 43. Configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d5, 5s2. Up to here, we have 10 electrons, 30 electrons, 36, 41, 43. So this is actually the configuration of technetium. Right? Actually, technetium is, if you consider, if you go group wise, after manganese, in the same group, the next element is technetium. So for the manganese also, we have same kind of a configuration as 3d5, 5s2. So therefore, we can easily remember technetium configuration if you know the manganese configuration, because we have learned that same group elements have same chemical properties, right? Always remember that one. Same group elements have same chemical properties, because where valence configurations are, their valence configurations are similar. Right, then this is forming a Tc 4 plus cation. So the 4 plus cation means you can tell that it is removing 4 electrons. We can tell that after removal of 4 electrons, the configuration is 4d3, 5s0. So 4d3 means in the d sub energy level, we know that 5 orbitals are there. So in these 5 orbitals, there are 3 electrons according to the Hund's rule. For each orbital 1, 1, 2, 3. So then we can tell that there are 3 unpaired electrons. They're asking the number of electrons in the last sub-energy level of the plus 4 cation formed from the element of atomic number 43. Students, this is the last sub-energy level. Last sub-energy level is 4D. So in the 4D sub-energy level, we can see that there are 3 electrons. Question number 5. Answer is third one. Very easy. Let's move for the question number 6. The electron configuration of cobalt is given 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. What is the valence shell electron configuration of cobalt 2 plus? Are you very easy? Cobalt is 27. They have given the configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. So it is forming cobalt 2 plus cation. We have learned that how to write down the electron configuration of cations also. So cobaltus, the name of this cation is cobaltus. So it is removing 2 electrons. So therefore the valence shell configuration is 3d7. Now 4s electrons are removed, therefore 4s0. Okay, so we can tell that the configuration is 3d7 or 3d7 4s0. So 3d7 4s0 configuration given in the third answer again. So therefore we can consider that. Question number 6 also. Answer third one. See how easy these questions are. Let's move for the question number 7. So question number 7, they have given what is the number of orbitals containing unpaired electrons present in the last sub-energy level of an element whose valence shell configuration is 4s2, 4p4. Students, if they have given 4s2, 4p4 configuration, you should be able to understand s orbitals are completely filled with the electrons in this. Then p sub-energy level containing 3p orbitals, and there are 4 electrons. Then let's fill the electrons according to the Hund's rule, one by one, 1, 2, 3, and here this is the 4th electron. They are asking what is the number of orbitals containing unpaired electrons present in the last sub-energy level of an element whose valence configuration is this. Now can you see that how many orbitals are there with unpaired electrons? Just 2, right? So number of unpaired electrons. First of all, you have to find out number of unpaired electrons. R2. So therefore, those unpaired are containing in 2 orbitals. So therefore, there are 2 orbitals. Question number 7, answer is first. Very easy. Okay, very, very easy. Let's move for the question number 8. Which of the following molecules contain equal number of electrons, neutrons, and protons? Remember, students, first of all, you have to know that in order to go for this answer, can you remember we learned that isotopes of hydrogen? There are 3 types of isotopes for the hydrogen element, right? Protium, deuterium, tritium. Those are the isotopes of hydrogen. What are they? Protium, hydrogen 1, 1. Then the next one is deuterium, hydrogen 1, 2. Then the next one is tritium, hydrogen 1, 3. These are the 3 types of isotopes of hydrogen. Now, when you consider the number of electrons, protons, and neutrons in each, here 1 electron, 1 proton, 0 neutrons. Deuterium, 1 electron, 1 proton, 1 neutron. Tritium, 1 electron, 1 proton, 2 neutrons. When the mass number changes, we can see that isotopes are obtained for that particular element. The neutron count is changing, no? Therefore, we have 3 isotopes. So in this question, they have given that they have given 5 compounds. Which of the following molecules contain equal number of electrons, neutrons, and protons? Very easy. Okay, let's go one by one. First of all, they have given H2O. Then they have given D2O, T2O. This D means deuterium, capital T means tritium. DOH, and the next one is HT. So let's count the electrons. Very easy. We know that in oxygen atom, how many electrons are there, students? 8. Neither. Then hydrogen 1. There are 2 hydrogen. Therefore, 8 plus 2. So the proton count is also same. Neutrons. We know that hydrogen doesn't contain in neutrons, but oxygen contains neutrons. How many? 8. So therefore, we can put it. We can see that electron, proton, neutron count is not same. So therefore, we cannot consider this one. D2O. How many electrons are there? We know that electron count is same as H2O. Proton, same. Now we can consider that oxygen atom is containing 8 neutrons. In deuterium, remember, we have 1 neutron. in the nucleus. There are 2 deuterium atoms, so therefore 10 neutrons are there in the D2O molecule. Can you see that all the counts, electron, proton, neutron counts are same? This is the answer. But anyway, let's check these also. Tritium, T2O. Electrons are same, protons are same. Then in tritium, we know that we have extra neutron, extra 2 neutrons. Okay? Therefore, we can tell that 4 plus 8 is 12. There are 12 neutrons completely in that molecule. So therefore, electron, proton, neutron count is not. DOH, we can see that 10 electrons, 10 protons. How many neutrons are there? In deuterium, we can see 1 neutron. In oxygen, there are 8 neutrons. So therefore, 9. And here also, electron, proton, neutron count is oxygen. HD, electrons are 2, protons are 2. Neutrons, 1. Why? Only deuterium contain neutrons. So therefore, answer for this question is question number 8, second one. Right? So here they have checked the knowledge of what? Isotopes, no? Number 9 is orbital diagrams. Let's see. One that shows the correct distribution of valence electrons of an element is. What do you think? Let me draw the 5 diagrams they have given. Okay, students, in the first diagram, you can see that this kind of a orbital filling. In the second one, you can see that the orbital filling is like this. Students, without filling for the second orbital, how that electron is going for the third one? This is not possible, right? Wrong. What about the third one? In this way. This is actually violating the Hund's rule. Why? I told you that according to the Hund's rule, always when the unpaired electrons are filling to the atomic orbitals, the same spin, the same direction electrons are filling. So if I consider this electron is rotating clockwise and this one is counterclockwise. If it is in the same orbital, now then correct me. This is correct, clockwise, counterclockwise, but that is in the same electron, same orbital. But here, 2 different orbitals. So when the electrons are filling to the atomic orbitals in this way, always parallel spin, same spin electron should be filled. So therefore, 2 direction, no, not correct. What about the fourth one? Look at the fourth one. Do we have this kind of a orbital diagram? Did I teach you this kind of orbital diagram? No, that is wrong. And here, so without filling is P as fill. So therefore, that is also wrong. So therefore, the correct one, the acceptable one should be this one. Question number 9, answer is first. So here they have tested whether you know the Hund's rule, how the electrons are filling to the atomic orbitals. Question number 10, which of the following arrangements of the electron is most likely to be stable? Stable electron configurations. Can you remember, students? I told you that When we discuss about the electron configurations, I told you that under important point, normally D5 configuration is half stable. Then I told you D10 configuration is full stable. Likewise, P3 configuration also half stable. P6 configuration is full stable. So these are the stable configurations. Understood? So here they have given 5 d orbitals and 1 s orbital. So actually, according to the answers they have given, you can see that the most stable configuration here, we can see that none of the orbitals, none of the d orbitals are none of the d orbitals are completely filled. We cannot find here D10 configuration. But did you see there D5 configuration was there? In the third answer, they have given all the 5 d orbitals are filled with just one electron as well as the s orbital. So this configuration belongs to chromium 3d54s1. Can you remember? So this configuration is stable. In order to obtain the greater stability, chromium's configuration is rearranged. Can you remember that? So therefore, this is the most stable configuration that they have given among the 5 configuration. Question number 10, answer should be third one. Another very easy question. Okay. Yeah. So this is the 6th RYM paper that we have to discuss. Okay. So students, you can see that in this paper, actually, I have mostly considered the electron configuration. Okay. In the next papers, you will see that quantum numbers and the previous lessons, actually, I will include them also. Especially in the next paper, you will see that the quantum numbers questions will be there. Right. Let's discuss quantum number questions. So this is actually one of the easiest papers that we have to discuss as in paper 6. Okay. So you should be able to score 10 out of 10 for this paper because this paper is not that much of a big deal. So continuously we can practice these kind of 10 MCQs weekly. I will include more questions for this one. Let's increase this one up to 15 MCQs later. So first of all, practice these papers, do these questions again and again. I will upload this recording to the WhatsApp group also. And if you have any doubts, tell me. We can discuss the doubts. Okay. Okay. Then let's meet on the next paper, RYM paper 7, with the RYM paper 7 in the next week class. Okay. Right. Until then, bye bye. Have fun.